My name is Quincey Koziol. I'm at NERSC, Lawrence Berkeley National Lab, the supercomputing facility there. And this presentation is a joint effort by Scott and Elena at the HDF group and myself and a whole bunch of people pitching in to patch up things along the way. We appreciate that. So I'm going to be sharing my whole desktop, and that'll allow me to go back and forth between the shell window and the tutorial slides. So if you have any questions, if somebody could flag me down, it's difficult to see the chat when I'm in full screen mode.
I will try to help.
Okay, thanks. So let's see. We're going to assume that this is a parallel HDF5 tutorial, that you have a reasonable working knowledge of HDF5, of MPI, and since this is HDF5, MPI-IO, a good idea of what collective and independent I/O mean. I'll explain along the way if necessary and if possible. And of course, we're giving you all the information, and the example programs are in C, but the interfaces for parallel HDF5 are available through other language wrappers like Fortran as well. And if the cluster is up, you'll be able to log in and do the same things I'm working on here. And otherwise, just please send questions in, and I will definitely pause and we can chat about what to do. So this is designed to give you a quick introduction to parallel HDF5. There's a lot of options, but we're going to kind of show you the most popular ones and some of the most popular pitfalls and optimizations. These links here have very nice information and recent webinars that you can review, offline and in your own time. But ideally, we can walk through things enough here now that it'll give you a lot of good context for some future learning and tutorials for yourself. So ideally, you'll come away with how to use the parallel HDF5, when to use collective and independent correctly for raw data, for data set elements, and how to avoid HDF5, what we call sometimes a metadata storm, or a denial of service attack on your file system. So here's the basic instructions. I'm going to move this window just a little bit so that people can still see it, but you can also see my terminal window while I do this. Hopefully we'll get enough of both. So log into the cluster, right? If you're available, if it's available for you and you've got your SSH key set up, you can follow along. I've already made a temporary directory, and I'm going to clone the Git repo with this command as well. I've already kind of done it a few times. So say, hey, great. In the tutorial, we want to be in the parallel hands-on tutorial directory. Here, these are all the files. And you can take a look at the README if you'd like to see a brief overview, a couple of sentences of each example program. I'm going to walk through them all, so I won't show you the README. But if you SPAC load the first, any instance of HDF5 is fine from SPAC for these demos. So load your first instance of HDF5. Stephen showed there's a lot available, but the first one, anyone is fine. And then run make here. And this is set up so that it works correctly on the cluster. But if you have a different scenario where there's MPIs in a different place or something, you may have to kind of tweak it a little bit on your own. So this will step through and build each one of these example programs that we're going to talk about today. I'll give everyone 30 seconds to log in and build. We can sit here and log through the screen output. Somebody put a chat here. Is this for me? Oh, you got it. Okay, so that's the Git repo. Elena sent that. I've actually built all these programs in another directory that my editing window's up already. So I'm going to interrupt this here in my temporary directory. I'll just do a quick example of the srun command here. So srun is a scheduler, and it's going to run. I'd like to use 4 MPI ranks, and I'm going to use this first parallel program that we compiled and built here. Pretty boring, standard stuff, right? Creates an HDF5 program, or sorry, file in this directory. And we'll go on and look at these files in comparison in the next set of slides. But just as an example, this is the basic set of things. Check it out, go to the right directory, load HDF5, run make, wait a little longer so everything builds, and then you'll be able to run all the examples alongside. So going on, we'll get started with the example programs themselves. So HDF5 has two fundamental aspects to it. There's data sets with raw data IO, the elements in the data sets themselves, and metadata, the namespace or what the groups and the attributes look like, what the data sets are named, how large they are. That's sort of metadata for files. So here we're going to talk about kind of scalable ways to operate on both aspects of that. So we're going to talk about how to perform parallel IO to raw data, and lots of times there's more options here for the raw data IO. You can typically perform IO collectively or independently. So this can happen at your choosing for a data set. And all the MPI ranks can read and write from those data sets or different data sets. It's all in much more choices available to you there. For metadata, all the HDF5, all the MPI ranks can access, so read all the metadata, but if there's any metadata modifications that need to be made, that has to happen collectively. We'll show an example about that, but just kind of upfront, the metadata, right? There's also some limitations about the kinds of data that you can operate on for parallel programs. In theory, this is possible. You could extend HDF5 to operate on variable length data types in parallel, but we just don't support that currently. It would be a lot of engineering work to happen. Same with the single writer, multiple reader, swimmer mode. We don't support that in parallel right now. And I talked a little bit about the metadata modes. So I think that covers all the fundamental basic differences between a regular serial HDF5 and a parallel version of things. But if you've got a question, just pop it into the chat and we can pause and talk about it a little bit more too. Even compression is supported in parallel on your raw data, as long as it's a collective operation to write it. Reading it could happen independently. All right, so here is the first set of example programs. All the example programs, the serial ones, don't have any sort of prefix, infix to them, and all the parallel ones are called par something. So I'm going to show the serial program here, and this is exactly this H5EX0, and it's a very, very, very simple HDF5 program, a very simple parallel or serial one. Basically, the entire program can pretty much fit on the same screen here in about 40 lines. So we declare our variables and IDs and things up here. You'll initialize your data buffer somehow. Here we do something trivial, right? Say, oh, let's create a file access. You can always see that in the naming here, a file access property list. And then we create an HDF5 file with that property list and receive a file ID back. Then using that file ID and a data space ID that we create here with this create simple operation, we create a data set with a certain name. It has a native int data type in the file. It uses that file space so we know the dimensionality. It's very hard to predefine all the possible permutations of integers. So we require people to set up their own data spaces. And then we do IO to it. We take the buffer of data. Here is one of the parameters to the dataset write call. This is the data buffer we initialized earlier. And we do the write, populate the data elements in the data set. and close everything down. It's very straightforward. Get a data buffer, create a file, create a data set, write your data, close everything. It's a very straightforward HDF5 program. So to take a look at what this looks like as a parallel program, this is basically the same program converted to use parallel HDF5. And you can see that by and large, things are basically very similar, except we initialize. Set up some MPI variables. So the communicator we're going to use in the info object. Then we initialize MPI and use the communicator to retrieve the number of ranks and the size of the world, MPI world that we have. We're going to have 4 for our examples. Same thing, data buffer, except this one is going to be local on each rank, right? Since we're running an MPI program, the data buffers are all local to whatever MPI rank you're running at. Here's the first significant difference you could do. This, for the last serial program, we created a file access property list. We didn't particularly set anything. We chose the defaults, which is the serial IO. Here we say set, this is a file access property list. That's what this means, file access property list, FAPL, sometimes we say. And we're going to want the MPIO file driver for our file. So we pass the file ID that we created into this call, and we tell it what communicator and info objects to use for the file. In this case, we chose MPI world. Very straightforward. Then we do the same thing. We pass that property list to our file create operation, except this time, since we're running in an MPI job and we've set up the file access property list to use the MPIO driver, this is a collective MPI operation. It requires everybody to participate in your file create, also file opens. And everybody will come in together and use this communicator that we set as a property and passed in as a parameter here to collectively open that file with MPIO. And from there on out, it's mostly straightforward still. We create our data space, create the data set that uses it. It's in that file that we created with the MPI parameters, and we write data to it. In this case, I don't show anything special. Everybody's going to write a buffer, and it's pretty much going to overwrite all the ranks one on top of the other because we chose to write the whole buffer from all ranks to the whole buffer in the data set in the file. We'll show some specialization about that, about writing subsets from different ranks. But just as a very basic, you can do this. I wouldn't necessarily say let's go send this much data to the file system all the time, but it's possible to do this. And then you close everything down and terminate your MPI program. That basically is the significant difference. So you can see that here if you wanted to look at the actual source code comparisons. You can see that with the diff command, which is part of what the slides are discussing, right? So we've added in, we use a different file name because that's convenient. We set up our MPI parameters, initialize things, use the communicator to set the file access property list, and then we finalize. Those are they're very obvious parallel differences for these programs. And then to run it, we use our, actually earlier I was using MPI run directly, so let's go back to PS run. 4 ranks, create our HDF5 file, and you could look at that with H5 dump, which is the utility to kind of display the output for our HDF5 files in kind of a user-friendly text output way. And you can see we've indeed created a file. That's the name we pass into dump, has the right data set name, and all the data is as we initialized it. So it's done the right thing. It's created the file. If we had run the serial version of things, so you don't need srun, you don't need MPI run, so serial program, you just run that. And that will go ahead and create a single HDF5 file that's just called sds.h5. You can see it's identical. So this is very common. The files in the file format that we use for parallel HDF5 is identical to the file in the file format, or at least you can make them identical to the files that you create with serial. The format's identical and the structure is up to you. So that's not an uncommon thing. Some people will set up basically a skeleton, an unpopulated without data version of the file in a serial program, or maybe with MPI rank 0, and then reopen it as a parallel job using the MPIO file driver, and then populate it with the data from their MPI application in parallel, and that all works just fine. Any questions here? First example. Okay, I'll continue. No, please. You comment on where the magic happens, why parallel HDF5 is possible, and so the difference between MPI parallel and thread parallel. So sure, Nicholas, if you want to unmute and it'd be a little more interactive, I would certainly welcome that if you'd like to. But I'll try to wing it too.
Yeah, can
so,
you hear me?
Yep, gotcha.
Okay.
So the difference in a sense is that all the threads are within one process, and they're just being executed by what we would think of as a serial program running on, a computer, a typical program. An MPI program is actually copies of that program running on multiple instances, cores or nodes spread across a hopefully larger system, and they all cooperatively perform I/O together using some parallel specific commands. So threading is local to a process within the process, and MPI ranks are between processes across processes. Does that help?
I guess my question is more is like, so there's some coordination happening to allow this kind of parallel access to the file system. And is the fact that it's possible with MPI and not with threads kind of something intrinsic to what the MPI kind of offers as a sort of API or abstraction, or is it just something to do with like what has been implemented in the library in HDF5?
I'd say it's not intrinsic to MPI itself. It's how HDF5 works. I'll talk tomorrow about thread safety efforts and concurrency efforts that we're beginning for HDF5. We can get a lot more detail about it then, but kind of in a nutshell, there's a lot of data structures in memory for each process. And when you have an MPI program, each program is a separate process, so it can access and manipulate its copy of those data structures at its own whim. When you have a multi-threaded program, everybody's accessing the same data structures in the same memory space, and therefore there has to be a lot more coordination and typically we use locks to provide concurrent access without corrupting things. So it's the difference between operating on the data structures in memory, sharing those data structures in memory, and not sharing them. In an MPI program, they're all segregated off from each other.
Gotcha. Thanks.
Sure. So in theory, you could, if we get far enough along in this thread concurrency effort, you could run a multi-threaded MPI program safely if the HDF5 library was multi-threaded concurrent safe. So we'll get to the cross-product space in a while. It's a lot of engineering effort, but it's possible. Okay, I'll proceed to the next slide, but please, add more questions. It's great. I think we're going to have plenty of time for the tutorial. I've only got another, 5, 6 examples to kind of talk about in 40 minutes. So we have plenty of time.
Oh, Quincey, there is 15 minutes break, so please don't forget about that.
How long do you want me to have?
Let's stick to the schedule, but if people want to stay a little bit longer, then yeah, continue. But you have 25 minutes now.
Got it. Okay. Yeah, I can do that too. That's fine. Great. All right. So we'll go to the next slide here, the next set of examples. So this is the serial version, no infix, and then the parallel version of a similar program and an improved parallel version of that program. So I'm going to move over here to this other window. I've already got these guys open. This is the serial version. This is the H5EX1. And the goal is to write out a file where there's a data set that has column-oriented data. And we'd like it to operate efficiently with serial, but we can see how it will go faster and then even better in parallel. So it's basically a long, skinny data set. And we're going to first look at each MPI rank will own one column, right? Everybody, so rank 0 owns this column, and rank 1, and then rank 2 and 3. And writes that out using a hyperslab selection in HDF5. So each data set, or each MPI rank, has its local memory buffer, and its local memory buffer is only writing out to a particular column in the file. There's a little bit of setup here in the serial version of things, so I'm not going to cover that in great detail. You can see that we create our data set, and then this is the serial version, right? So we select a column, and we're going to iterate over all the columns, all 4, dim1 macro is set to 4. We're going to iterate over those columns. We'll select a column in the file, a column in the memory, and then this is the column in memory. So we created a memory space for it, and set up the buffer for performing the write, and then do the write. And here independently is a little bit of a misnomer. It's serial, everything is independent. And close everything down, and we'll iterate over that loop of 4 times, and just kind of a straightforward serial program. And maybe we'll show that as kind of a find it back in here. This is the example 1 program, and there's going to be a lot of output. This is a long, skinny program, or skinny file. You can basically see each column has a separate set of information in the data set. Going back here, this is the straightforward, independent version of that same program, basically. All the ranks collectively, everybody together, right? It's collectively all the ranks, create the data set. They've already opened the file, and we've talked through that. Then this rank sets up a memory space that covers a column. And in this case, we've queried out the MPI rank. So rank 0, this variable, MPI rank, will be set to 1, and then rank 1, it'll be 1. And 2, same thing, right? So each rank has a different starting point, a different column to perform its IO on. And each rank therefore selects a different hyperslab in the file, in the file's memory data space. Doesn't really matter about the memory space because everybody's got their own private buffers, but we set them all up identically. Populate the buffer with the data value for our MPI rank. So rank 0 will be writing 0s, rank 1 will be writing 1s. And then we, without any particular coordination, everybody writes out their column, right? So this all works just fine. It's just not the fastest thing in the world. I don't know how long we would have to wait for this to populate, but it'll eventually create a file, and it'll look identical to the previous serial file. So I'm going to interrupt it here because the next version is better. This version of the source code, PAR-EX1B, we should come up with that name, does all the same setup, creates that data set, still obviously collective, everybody has to set up the data set. Still does the same rank-based hyperslabs in the file, then does this special thing. This creates a pcreate, a property list create call, where it's creating a dataset transfer property list. Gets the ID back and then sets the special setting in this DXPL, dataset transfer property list, for MPIO operations. And we're going to say, hey, any MPI operation that I use this DXPL for, this dataset transfer property list, I want that operation to happen collectively. Everybody, all the ranks in the MPI job will get together and they'll coordinate to write that data out efficiently. And then every rank performs a write, but it uses that dataset transfer property list when it's writing its buffer out. You can see that this guy is going to run a lot faster than the previous one because all the ranks have gotten together, they've coordinated, and they've, MPI has optimizations to make nicely these interleaved IO patterns go quickly and head out to disk. So many times, collective IO is a good option for improving performance of your dataset IO, writing or reading, both. It's not a panacea. It doesn't solve every problem. It just says, hey, all the ranks are here. Try to optimize this. So there are times where collective IO will not go any faster than independent IO, but it's a good option. If all your ranks are there and it's possible, and you're not going to, twist your source code in your application in a particularly bad way, at least gives the ability for HDF5 and MPI to try to make as many optimizations as it can, because everybody's here and they can use the fast interconnect of the machine to transfer data instead of trying to coordinate through the file system with things. So that's the point here in our slide. The default properties, which is independent IO, it may not be optimal, right? You could see it as a greatly different speed that you achieve when you get this collective in there. And so you should consider the collective IO for reads and writes for your dataset elements. Any questions about this? Okay. I will proceed. So the next example is very similar. We have the similar output format for the dataset, except this time we're going to use the ability that HDF5 has to compress raw data IO. So we want to take a look at these two example files and see the difference between them. So it's still going to use collective, but we're also going to compress for our data set when we create it. So several things are just a little bit different here. We still create our file the same way we've always been doing, except this time we're going to use a dataset creation property list, a DCPL, right? That we create that property list, and we're going to say, hey, I'd like this dataset to be blocked up in pieces when it's written out to the file. We call that chunking in HDF5, and we choose some dimensions for our chunks here. And in this case, we're going to choose a column, an entire column, as one chunk. So each rank will be writing out one nice contiguous block of data in the file. Its chunk will be a column. So we set that up in the file. We say, hey, by the way, also compress each chunk. We choose deflate, zlib, deflate algorithm on our data set and tweak it up to 9 here, right? Then we go on and create the data set collectively, same operation, except now we've set some special properties for that data set creation to use chunking and to compress. You can choose compression without chunking, but compression requires chunking. So if you want to compress, you have to have chunking. And then we go basically the same setup. We initialize everything. We choose our column based on our MPI rank. So that's nicely lined up with the chunks that we've created as well. And then we perform a collective operation to write our data set using that data set transfer property list. Same set of writing the data out pieces. It's all in the creation part for chunking. You can see here that the file we create is a lot smaller. The files that we have been creating with this data set in them have been around 7 meg-ish, right? But when you compress it, it's obviously trivial data, right? It's all ones or all zeros. It compresses awesomely. And of course, you can see that the file we get with that parallel compression actually was quite a bit smaller. But this is how to do it, right? And you can see the benefit of it too sometimes. I wouldn't expect this on normal floating point data from a simulation or something like that. You might get 2 to 3x, depends on your data, of course, typical for compression.
Hey, Quincy, this is Alex. Quick question for me. Can you clarify the relationship between the chunks and the MPI ranks? Earlier, I think you said that the chunks, or that in this case, you do it so that one chunk corresponds to one rank. Is that a fixed requirement, or what's the relationship there?
It's not a fixed requirement. You can set any arbitrary chunking you'd like. It could have made rows or something really kind of bad in a sense, right? The chunks could have run this way and I could have written this way, and then you'd see really bad performance, really bad performance. That works, but I was trying to say, okay, we're going to steer towards an optimal, the most optimal way to do this. So I made, I say, oh, I've got my data set's so big and I've got so many ranks. Let's choose the chunk size to be a very nice match with my ranks and my data set.
Okay, that makes sense.
So I tuned it, right? 3 or 4 times.
Okay, thank you.
Yeah, sure. So this is actually the kind of one of the #1 questions I get on people is, oh, that's chunks are great. What do I do if I don't know what my eventual read or possible writes are going to be? How big should I make my chunks? And to be honest, I have no idea. It all depends on your access patterns, right? I tend to tell people, if you don't know any better, use the square root of the dimension you're dealing with. So if you had 100 by 100 data set, square root, 10 by 10 chunks is probably reasonable, right? 1,000 by 1,000, you'd get 30-ish by 30-ish sized chunks when you take a square root. It's not bad. If you don't have anything else to plug into your algorithm, it's not bad. It's much better if you have a sense of what your IO patterns are going to be and then tune your chunks towards that, like this one. We really could tell, oh, we've got 4 ranks, our data set is 4 rows or 4 columns. Boy, we should really tune it towards that. Chunk sizes, yeah.
I don't know, you intentionally skipped example C, because example C showed how chunking helped with independent IO.
No, sure. No,
comparing when we had to use collective to write the stall data set. So if you use chunking by column, then even with independent, it performs really well.
Okay, yeah, sorry. Now my screen has done something odd. Why are you not? Did we lose the cluster? It's no longer doing anything.
It is possible.
Good. Oh, no, still here. Okay, good. For some reason, it's just not responding to VI in this window.
And it doesn't respond to LS for me.
Okay. Well, yeah, sorry, I would have gone back to that, but I don't know what we're going to do here. Let me see if I can go to the next one. It's just not. Screen is working, but VI is not.
It's something to do with the similar denial of service attack. The setup would be normally separate the IO server for the jobs.
Okay, so maybe it's just
get the resources.
High load or something.
Yes,
blocking this. Okay, so well,
the need as well on the lower level.
Okay, no problem. I will talk to the slides. People can experiment with the Git repo, and we can, do it a little more detached from the cluster.
Would you like to log in Jelly? We have all programs there. I can send you where to go.
I think it would be difficult in 10 minutes.
Okay.
Yeah, I've got about 4 things left. I can cover them, but It's fine. So we'll just talk to this.
You can go to RIPA and show examples there. Use your browser.
Maybe.
Make it slightly bigger and then.
Yeah. I had this all the other windows and all the other files queued up. Everything was ready, but we can do it this way. All right, so let's try not to overlap slides if we can too much. All right, so when I started out, I was talking about how changing the structure, the namespace of a file, has to be done collectively. And were we able to run these well, we would be able to see that that's indeed true. And you get different output when you modify things collectively versus independently. But so this example, the EX2A, is making each rank create a group with a different name. We're basing the group name on the rank and then creating that group. In this case, you may get hangs, but in a very simple program like this one, you'll get kind of the last writer wins. Whatever output you would get from this, running this 2A program, one of these groups would exist and the other three wouldn't. It would be incorrect, probably, for your application, and probably a little random. Whichever guy, went ahead in the scheduler a little bit quicker and launched that process would get out first, write some data, and have it get overwritten by everybody except the last guy, and the last guy will go. But if you look at the second program, the 2B program, you can see that instead of each group getting created by a single rank, all the groups iterate over the number of ranks in the MPI job, MPI size, the size of MPI world typically. They all create a group with that name. So they'll start at 0, group 0, and then group 1, then 2, 3, right? And create groups and data sets within them all together. It's all collective, it's all the same order, it's all the same set of file groups and data sets in the file, and you'll end up with a grouping structure in the file that looks like what you'd expect, what you'd want. Once all these namespace changes are done, you can actually write to those data sets independently of one another. So if that was important to you, you just need to set up the namespace first, and then you can do I/O on an individual data set on each rank independently of the other ones. So again, your program will hang eventually. You'll get this strange hang because MPI is caching, or I'm sorry, HDF5 is caching metadata changes, and eventually your caches will drift out of sync, and somewhere later on from where you didn't make the collective call, we're working on this, somewhere later on, you'll get a hang. It's like, gosh, this HDF5 call hung, and I don't understand, it looks fine. That's because like 43 calls earlier, you didn't do something collectively. It's unfortunate. But there is a list of all the calls that you do need to make collectively here at this URL. So it's basically anything that modifies metadata in an HDF5 file. Here, somebody's pasted, it's from Elena. Yeah, you can see in the chat window that, a race condition where one of those groups was created, but the other ones weren't from the 2A program. So let's see. So reading in parallel programs is very straightforward, right? And it's always independent of one another, except the collective call, right? The collective file open, everybody's got to open it together so that they all do that MPI file open with the same communicator at the same time. And after that, you can open and close attributes, data sets, name data types, and of course, as long as you don't change anything about the file, right? So safe way to do this is to open your file in read-only mode and then go ahead and just iterate over things in the file. Do we have the next one? Yeah, that's fine. Okay, so these last 3 slides talk about parallel metadata issues. So let's go ahead and do that, right? This program, the 2D, opens a file collectively. So it creates a property list, sets it to use ComWorld, and then creates the file, populates all those objects in the file in the namespace, and then closes the file, right? So this is how to create a file collectively, right? That's the 2D one, and then the 2E one is going to go iterate over that and look at things. And this is the independent part. Aside from the file open, which has to be done collectively, everybody can open any group they want, right? So based on your MPI rank, you open the group you're interested in, open the data set you're interested in, look at its name if you feel like it, write some data to it even, that's fine, because it's the data elements, not the metadata, the structure of the file. And then close everything down. Totally fine. And if you want to, the parallel version of things tends to choose the allocation time early, but this is not the default for sequential. So if you want to create the skeleton file first and then open it in parallel, you need to set the allocation time, which controls the data set elements allocation in the file, and you have to set that to early to allocate the file and space in the file. And of course, this doesn't work for things you change at runtime, right? So if it's extensible and you're going to be changing it with the writer, well, of course, you can't create things that are still future-based. And same with compress. You're going to write data, the compressed data has to be written collectively, and that's a requirement for that as well. So you can't use independent I/O for those guys. So the final one final example here is this comparison source code, and we use the bank file to create 3 variants of this as an executable. But let me look at the source code here. This source code is compiled with a couple of macros to compile in or compile out things when we build these executables. So this example code is describing, trying to teach about how to improve those parallel open calls, the operations that occur. These 2 calls in particular say, hey, when you operate this first one, set all collective metadata ups on the file access property list to true, which is 1, right? Saying, I promise. This is a promise that the app makes. We have no way to enforce it, and you'll probably get hangs if you don't, live up to your promise. You say, I promise that all ranks will read the same pieces of metadata from the file. So they'll perform the same metadata operations like opening or creating data in the file, extending data sets, those sorts of things. And likewise, HDF5 is allowed to perform collective metadata writes. So it should be able to make MPIO collective operations for its metadata. And these 2 guys taken together say that, hey, whenever I work on this HDF5 file, it's all going to be in lockstep. Everybody's going to read the same things. Everybody's going to write the same metadata. It's all going to be fine. Might change the different hyperslabs to write out actual data set elements, but all the metadata operations that actually deal with namespace objects like data sets and groups, that's all identical. And that lets HDF5 perform optimizations about, great, rank 0 will read that piece of metadata in for you, and we'll broadcast it using MPI over to the other ranks. So they don't have to touch the file system. Otherwise, everybody would have to go down to the file system, look at the piece of, read the piece of metadata, put it in their metadata cache, and go on with their program's execution. If you set this collective metadata ops property for your thing, you're saying, I promise everybody will be reading data set or metadata from the file identically. So therefore, HDF5 can do that read on rank 0 and bcast to the other ranks. That optimization is important because when you have hundreds of thousands of MPI ranks on a very large system, and they all try to go to the file system to go read a small piece of metadata, it would be awfully nice if we could use the interconnect to broadcast the metadata. Instead of 100,000 reads occurring, we get one with this optimization. So when you have a chance, you'll probably find that this comparison code runs very, very slowly because it's, at least at scale. Every rank is reading the same bits of metadata and it'll run very slowly. When you run the version with this optimization enabled, you say, boom, fast. It's really straightforward. And this example is very similar, and it shows collective IO on the raw data, the data set elements themselves as well. You can see that down here with this macro. But we've covered this a little bit already. So, hey, set the data set transfer property list to use collective IO when I do my write. So other hints here, yeah, try to use the latest version of HDF5 in general, because we're going to keep up and keep optimizing things. We find new things all the time to go speed up. Generally very important to try to stay with the latest stable things. And if you have a chance, and this is a little more unusual for parallel programs, but if you have small data sets, it would be a whole lot faster if you used what we call compact storage, which kind of folds the data up into the metadata place, the object header for the data set, and performs one IO instead of two when you read and write that data set. So that, again, will help avoid these metadata storms. So I'm a couple of minutes over, but maybe we have time for a couple of questions while we take a break too.
Yeah, thank you, Quincey. Yeah, I suggest if there are questions, let's go with the questions, and we'll start in 13 minutes with our last presentation. Okay. So please go ahead with the questions.
And just unmute or put them in the chat either way, it's fine.
Okay, so we're around, so if any questions come up, please use chat window or just send it to us. Thank you. So we'll meet in 12 minutes. Oh, there is a question.
Yep, I think it's just for the slides. So Elena, it's the version that's on SharePoint if you want to push them to the repo.
Yeah, I will do. And there is a question from Gwen Muller. When an operation is collective, and there's another one. Do you see them?
So yeah, I got them off to the side now. So it says when an operation is collective, does each process wait on that operation? Tricky question in a sense. Collective in MPI, the MPI world, right? The semantics of it means everybody has to call it. It doesn't always mean that it's synchronizing, and it doesn't always mean that there's any communication at all, even a non-blocking kind of communication. It merely means that at the very minimum, some state has to be the same on every MPI rank. Now, because everybody does get there, it's collective, right? We can do optimizations at that point, but there can be runtime decisions about whether it does do an optimization or not based on the state of the program at that point in time. So many times collective operations are synchronizing to some degree, but it's not a requirement. There are times where we look at the state of the program, we go, well, it would be really better off if everybody just went and did their own IO. We're doing gigabyte sized IO, they don't overlap, they don't interleave. Just go ahead and do your write on your own. It's perfectly fine for you to do that. So everybody kind of checks in. Everybody has to look at the IO operation, but there's maybe not even communication between the ranks. It just, decides not to communicate and it just to perform IO. So hopefully that helps. If it doesn't, give me another message. So Celso, is there a way to see the MPI calls under the hood of an HDF5 program? not as directly, but you can, and I know Celso is familiar with it, but you can use a tool from Argonne National Lab called Darshan, D-A-R-S-H-A-N. I could put it somewhere in the chat maybe. And that allows you to log the POSIX, MPI IO, and HDF5 calls that your application is invoking. So you can at least get some level of tracing out of it. It's not as simple as this data set corresponds exactly to this HDF5 MPI, or I'm sorry, this MPI IO call, but it can get you into the right ballpark. So
Okay, thank you.
Yeah. Future direction of, so there's a picture of the ecosystem hierarchy. I'm not certain about that one. And future direction as far as relationship of parallel and HSDS. That's an interesting question. Parallel HDF5 tends to be used, of course, in MPI environments, pretty exclusively HPC systems, but cloud is kind of eating some of that, right? So I don't know, John, do you want to think about, we certainly don't normally support MPI in an HDS environment. It would be possible.
Right. I can jump in here a little
Sure.
bit. I can talk about this tomorrow too, but with HSDS, there's some additional options, right? So MPI, to my understanding, is really good when you need kind of like tightly coordinated multi-process, multi-machine types of workflows. HSDS works with loosely coordinated things, right? So you could have, say, 10 containers running, and each container is updating different parts of an HDF5 dataset that's shared between those containers. So as long as the clients divvy up, so they're not like overriding each other's data, that'll work. So it's kind of like a multi-writer, multi-reader type of scenario, which doesn't work with the HDF5 library, except in the MPI parallel HDF5. So again, we can talk more about this tomorrow.
Yeah, it's the tightness of the coupling ultimately, and the is everybody here kind of at the same time, which is kind of the same thing in a way. But, yep. So Luca says parallel reading. So basically all the things that I mentioned here for parallel writing, the collective IO and those kinds of operations would apply to a, reading a 1D slice out of a 3D cube from each rank. So each rank would describe the hyperslab that they were interested in the 3D cube for that MPI rank. And then all the ranks would come together and make a collective dataset read call, basically using this same call, right? You'd say set DXPL and BIO, you'd have selected a hyperslab, actually this one here in the file, right? Everybody would select a different hyperslab in the file, choose collective IO, and instead of a write, you'd have a read. But at least it puts all the ranks together, and that's HDF5 and MPI. See if there's something it can do with exchanging data between the different MPI ranks in order to speed that operation up. And in a case like you're describing, where one slices out of a 3D cube, it's pretty likely that at some point you can get the whole 3D cube on one rank or another, and then broadcast out the slices. Depends how big the 3D cube is. But at least when you do that collective setup and all the ranks come into the dataset read together, you at least give the options to HDF5. If you did this independently, we'd just have to go out and go to disk and get your data by ourselves without trying to coordinate or optimize with the other ranks. So, Luca, does that help? Cool. All right. Anyone else?
Thank you, Quincy.